εισαγωγή εγώ και μετά θα δώσουμε το λόγο στον Σπύρο για να ξεκινήσει την παρουσίασή του, έτσι.
Εντάξει.
Λοιπόν, dear colleagues, I'd like to welcome you all to this presentation of Mr. Spyros Murta's dissertation entitled Intelligent Online Optimization Algorithms for Portfolio Analysis and Management. I would like to start with a few words about Spyros and our cooperation. I first met him as one of my students in the master thesis program Mathematical Finance and Risk Analysis of our department. He attended all the mandatory courses provided by our curriculum dealing with mathematics, statistics, informatics, and finance. He worked very hard with dedication in all of them and achieved high ranks. He showed a particular interest in applications of mathematics and economics from the start of his studies. And by the end of his postgraduate studies, he prepared and submitted and then published two interesting papers, one in applied mathematics and computation and the other in computational economics. Following that, we began discussing a possible PhD dissertation, and finally, we submitted a PhD proposal to the Department of Economics at the National and Kapodistrian University of Athens. Since his proposal was accepted, he began his PhD studies in November 2019 under my supervision, while his three-member committee includes two excellent researchers and colleagues, Professor Stanimirovic from the University of Nice in Serbia, and Professor Tsipras from the National and Kapodistrian University of Athens. During his PhD studies, Spyros participated also in the Erasmus Plus program and transferred for one semester to the Department of Computer Science in the University of Nice in Serbia for the elaboration of his research. Also, it is worth mentioning that his PhD studies were supported by the Stavros Tsakirakis Scholarship. I have to mention that throughout the previous 3 years, we have worked on his thesis almost every day, had endless talks about different topics, and all of this has resulted in an excellent, in my opinion, PhD dissertation. Now Spyros has co-authored about 40 articles in international peer-reviewed journals, as well as 2 book chapters and 3 conference papers. 10 of the aforementioned publications are included in his dissertation, 9 journal papers and 1 book chapter. So here we are at the final frontier of this interesting scientific journey. In the next several minutes, Spyros will support his scientific results. So, Spyros, it's your turn now.
Okay. Hi, everyone. I will present you my doctoral dissertation with title Intelligent Online Optimization Algorithm for Portfolio Analysis and Management. Before I start, I would like to thank my supervisor, Professor Vasilios Katsikis. Throughout the course of my work, his essential guidance and suggestion in dealing with the difficulties I faced were catalytic. And also, I would like to thank my committee members, Professor Predrag Stanimirovic and Professor Haralambos Tsitouras, whose expertise, guidance, and encouragement have been beyond valuable for both the work of this doctoral dissertation and my academic development. In this dissertation, we took a popular financial problem and converted them into time-varying financial problem. And then we categorized them into time-varying linear programming problems, time-varying quadratic programming problems, time-varying non-linear programming problems, and time-varying integer linear programming problems. So the first 2 problems, we addressed them with neural networks, and we find their online solution. And the last 2 problems, we approach them with meta-heuristics, and again, we find their online solution. An online solution consists of consecutive solution with the feature that the previous solution is used as an initial input instead of a random input at each solution iterative process. And in this way, it reduces the time consumption needed to generate a regular solution to a time-varying problem. In the literature, due to the high complexity of time-varying optimization problems, the time-varying attempts to solve financial problems restrict in solving the corresponding static problems sequentially. So, in finance, a portfolio is defined as a group of financial assets that investor holds. Portfolio optimization is considered as the optimal allotment procedure of assets according to specific objective parameters such as return maximization and cost minimization. Optimizing the portfolio consequently plays a role of great importance in financial decisions. Our set focuses on popular portfolio selection problem, which are the Markowitz mean value portfolio selection, or for simplicity, MVPS, the Black-Litterman portfolio optimization, for simplicity, BLPO, the tangency portfolio, and the minimum cost portfolio insurance, for simplicity, MCPI. So we compared this problem with time-varying optimization problems, and we classified them into three categories, which are the mean variance optimization, maximizing the sub ratio, and minimizing the portfolio insurance cost. So it's important to mention that the innovation of this doctoral dissertation is the conversion of the aforementioned popular financial problem into time-varying analogs of the static ones, as well as the approaches that we developed to solve them. So we move on to the time-varying mathematical problem formulation. And we start from the time-varying quadratic programming form, or for simplicity, TVQP, which is presented in equation 1 to 4. In equation 1, we have the quadratic function, objective function. Equation 2 is the inequality constraints. Equation 3 is the equality constraints, and equation 4 are the lower and upper boundaries of the main variable. So it is crucial to point out that the TVQP form is transformed into time-varying linear programming form when g of t equals 0. Next, we move on to the time-varying nonlinear programming form, which is presented in equation 5 to 8, where we have in equation 5 the objective function, equation 6 is the equality constraints, equation 7 is the inequality constraints, and the domain that the main variable is presented in equation 8. So one of these functions, at least one of these functions, must be nonlinear. It's crucial to point out that the TVNLP form is transformed into time-varying integer linear programming form when the function f, h, and j of x of t are linear and x of t belongs to the integers domain. Next, we move on to the neural network solvers, which are the zero neural network, or for simplicity ZNN, and the linear variation inequality-based primary neural network, or for simplicity LVI-PDNN. So both of these solvers are originated from the Holpit network. Holpit network or gradient neural network is a recurrent neural network having synaptic connection pattern, such that there is an underlying Lyapunov or energy function for the activity dynamics. Started in any initial state, the state of the system evolved to a final state that is a local minimum of the Lyapunov function. The main use of the Holpit network is as associated memory because the stored patterns are encoded as the weights of the network. Modern Holpit networks or dense associated memories can be best understood in continuous variables and continuous time. So the ZNN was introduced by Zhang back in 2001, and it can be studied theoretically and has been proven to be effective and reliable tool for solving time-varying problems. So by setting an error function E of t, and then using the dynamical system presented in equation 9, it is shown that E of t is compared to exponentially converge to the null matrix. So considering the TVQP form that we aforementioned, we reformulated and to the form that is presented in equation 10 and 11. So we exclude the inequality constraints and we added a penalty function that includes that inequality constraints in the objective function of equation 10. Then, as usual, we use Lagrange multipliers. So we set the Lagrange function in equation 12, and then we want to zero the partial derivatives of this Lagrange function in terms of x of t and lambda of t. As a result, we set e sub 1 of t as the Lagrange function the partial derivative of the Lagrange function in terms of x of t, and we also set e sub 2 of t, the partial derivative in terms of lambda of t of the Lagrange function. As a result, setting e of t, a vector that includes e sub 1 of t and e sub 2 of t, we are able to solve in terms of the time derivative of x of t and lambda of t in order to produce the line solution of the TVQP problem. Next, we move on to the LVI-PDNN solver, which is also based on the Lagrange multiplier method. First, we have to define the following coefficient, which are presented in this slide. These coefficients are the capital H of t, and the primal dual decision vector C of t, as well as the lower and upper boundaries, which are the var sigma to minus of t and var sigma to plus of t. Then, by using the projection operation P sub omega, presented in equation 15, we use a dynamical system in equation 16 in order to produce the online solution to the TVQP problem. It is important to mention that the doctoral dissertation goes into great length about both these NNN solvers, theoretical background. So next we move on to meta-heuristics, where we are going to see the Biddle-Asena search algorithm, or for simplicity BAS, and its variation, as well as dealing with constraints. So intelligent algorithms are practical alternative techniques for tackling and solving a variety of challenging problems. Nature has been an inspiration for several meta-heuristic algorithms being introduced. Without being told, but by experience, it has managed to solve problems. The principal inspiration behind the early meta-heuristic algorithm was natural selection and survival of the fittest. There are several meta-heuristic algorithm options in the literature, but the current research will compare the effectiveness of the BAS algorithm and its variation, which are the binary BAS, the V-shaped BAS, the semi-integer BAS, time-varying BAS, and the time-varying auto-penalty BAS, with the following efficient and popular algorithm, which are the Firefly algorithm, the BAT algorithm, the binary BAT algorithm, the differential evolution, particle swallow optimization for simplicity PSO, the V-shaped PSO, the slime mold algorithm, the MATLAB genetic algorithm, the binary genetic algorithm, and the MATLAB's fmin function. So the Biddle-Asena search algorithm mimics the searching behavior of the Biddle. Assume that the Biddle position can be represented by the variable x, and x sub L and x sub R are the position of the Biddle's antenna. So the objective function measures the dense of the order. So the Biddle takes time instant t and measure the order of the source of the food source. So the Biddle goes to the direction by a step size delta where the order is higher. So eventually, after several iterations, the Biddle eventually reaches the food source. So to mimic this behavior, the Biddle searching random path is presented in equation 17, and the Biddle left and right antenna behavior is presented in equation 18 and 19. So the detected behavior is presented in equation 20, and the updated rules are presented in equation 21 and 22. There a diagrammatic representation of this algorithm is presented in this figure. So this algorithm is in general very simple and very fast algorithm. So all of these meta-heuristics are capable for unconstrained optimization. So the penalty method are used, which try to convert a constraint optimization problem into an unconstrained one by incorporating its constraints in the revised objective, which is present in equation 23. And next we move on to the application in a real-world data set. Before I continue, first I must to say some general notation. So by X is the market space, X sub I denotes the I asset price, TAF denotes the number of delays, T denotes the time, C of T is the covariance, R of T denotes the expected return of the market and has the properties of the moving average, R sub I is the expected return of the asset I, RP is the targeted expected return of the portfolio, eta of T is the optimal portfolio, and the bold 0 and 1 denote the 0 and unit vectors respectively. So we'll start with problems based on the mean variance optimization. The factor to measure risk is the variance of the portfolio. Then smaller the variance, lower will be the risk. And this approach was introduced a few decades ago by Markovitch model portfolio theory. The Markovitch MVPS is widely considered as a significant investment strategy. So our first problem formulation is the time-varying MVPS problem with specific expected return target, or for simplicity, setup, where we try to minimize the risk of the portfolio in equation 24, and at the same time, we try to keep our expected return in a specific target return in equation 25. More information for each problem formulation you can see in the footnote of this slide. The second setup is the time-varying MVPS problem with all possible expected returns, or for simplicity, a paired setup. But again, we try to minimize the risk of the portfolio, and but now we want to have an expected return above the target return, as is presented by the inequality of equation 28. So in this application, we use a market of 4 stock prices, which is presented in figure 2. So figure 2 includes a ticker symbol or symbol stock, which is an arrangement of character that used for identification of a bond, stock, or any other security trading on the stock exchange. So every listed security in financial market has a unique ticker symbol. So for presentational consideration, we will display applications that have small portfolios. However, the doctoral dissertation also contains applications with larger portfolios. So the market of this application includes 4 stock prices from April 2019 to October 2019. So given an initial portfolio and using the setting presented in this slide, the results are the following. Figure 3a shows the portfolio weights where we compare the neural network solvers with the quad-proc function. So it is significant to note that the literature of these neural network solvers frequently consider the MATLAB function quad-proc solution as the theoretical solution. So that's the reason that we compare the solution of these solvers with quad-proc. So as you can see in figure 3a, the ZNN, both the neural network solver produce identical solution with a quad-proc function. So figure 3b shows the portfolio risk, where we can observe that between the period June and August, we have a high risk. Figure 4a shows the portfolio expected return. We can see that the portfolio expected return is above the target return, and at the same time that the expected return is lower in the period June to June. Figure 4b shows the error between the neural network solvers and the quad-proc solution, where we can observe that the ZNN solution is closer to the quad-PROG solution than the LVI-PDNN solution. So it is important to mention that the ODE solver is used under the default settings. So an error between an error of 10 to -4, 10 to -5 is expected. However, if we adjust the absolute and relative tolerance of the ODE solvers, we can have a much lower error than 10 to -4. So next are the result of the time varying MVPS problem on the aperture setup. Again, figure 5A shows the portfolio weights, and the solution of the ZNN and LVI-PDNN is identical to the solution of quad-PROG. So figure 5B shows the portfolio risk. Again, for the month June, we have a high variance, so have a high portfolio risk, and the portfolio expected return is above the target return and also above the simple moving average 20, as shown in figure 6A. Figure 6B shows the error between the solvents, and now we can see that the LVI-PDNN produces a solution much closer to quad-PROG than the ZNN. So next we have the time consumption of the solvers presented in table 1, where we can see that in both setups, ZNN produces fastest result for the nearest neighbor and linear interpolation method, while the LVI-PDNN produces the fastest result for the interpolation method piecewise cubic Hermite and cubic S-spline. At the same time, quad-PROG was the slowest method used. Next, we move on to the time-varying Blank-Liedermann problem, Blank-Liedermann optimization problem, which is presented in equation 31 to 34. It's important to note that in the Blank-Liedermann model, investor views about future asset return are taken into account in contrast to the Markovits mean variance model. So here we try to minimize the equilibrium returns covariance in equation 31, and at the same time to keep the portfolio equilibrium returns above a portfolio return bracket in equation 33. So the market in this application uses the stock prices that presented in figure 7A, where we used the portfolio of 4 stocks for the period May 2020 to September 2020. 2 of these stocks include investor views, and the other 2 stocks don't include investor views. It is important to mention that the investor views are generated by a feed-forward neural network, so they are prediction based on a neural network. Then, given an initial portfolio and using the setting presented in this slide, the results are the following. Figure 8A shows the portfolio weights, where we can see that the neural network solvers produce an identical solution with a quad-PROG function. Figure 8B shows the portfolio risk, where we can see that we have a high risk for the July month. Figure 9A shows the portfolio equilibrium return, where we can see that is general above the simple moving average 40. And figure 9B shows the error between the neural network solvers and the function quad-PROG. Again, we can see that ZNN produces a solution much closer to quad-PROG solution. Next, we move on to the time-varying MVPS under transaction constant cardinality constraint problem, which is presented in equations of these slides. The first equations, in the first equation, we try to minimize the portfolio risk and at the same time the transaction costs. And with the K capital, we denote the cardinality constraint number. Also, the upper boundary of this portfolio, it is the maximum amount that an investor can hold for each stock if he invests all the pay of the portfolio payoff in the specific asset. So next, we are going to define the transaction cost, where we consider that K/buy of t equals 0 if no transaction is made. Otherwise, the K/buy of t equals a fixed cost and a cost plus a cost price associated with the sale or buy of the asset I. So figure 10 shows the fixed plus linear function of the transaction cost. Notice that this function is explicitly non-convex with the exception of zero fixed cost condition. So in this application, we use the stock prices of the stock present in figure 11. So the market includes four stock prices from the period October 2018 to January 2020. So given an initial portfolio, using the setting presented in this slide, the results are the following. Figure 12a shows the portfolio weights, where we observe that each algorithm produces a different portfolio. Figure 12b shows the portfolio risk, where we observe that the performance of all the algorithms is pretty similar. Figure 13 shows the expected return, and figure 13b shows the transaction cost. Of course, again, we can observe that all the algorithm produces similar results. But in table 2, we can see we have measured the performance, the time consumption of this algorithm, and we can see that the time varying mode to penalty bus, it's much faster than the rest of the algorithm. So the TVO to bus is most efficient than the rest of the algorithm compared in this application. Next, we move on to the time varying binary Markov-Bates problem, which is an NP-hard problem, and is presented in equation 39 to 42. So in equation 39, we want to minimize the portfolio risk and at the same time the transaction costs. And in equation 41, we want to keep the maximum amount of the asset an investor can hold between a specific range. And this is a binary problem. So in equation 42, we can see that the main variable can take prices only 0 and 1. So in this application, we use the stocks presented in figure 14. So we included the Dow Jones Industry Average Index component companies, which are 30 companies. So we have included in the market 30 stocks from the period December 2019 to January 2021. So given an initial portfolio and using the setting presented in this slide, the results are the following. So figure 15a shows the average of the objective function, where we can see that VS bus has the lowest average price, while binary bus has the second lowest average price. The portfolio risk is present in figure 15b, where we can see that all algorithm has a similar solution. Figure 16a, we have the expected return. We can see that all the expected returns are above the target price. And figure 16b shows the transaction cost. Table 3 shows the time consumption of the algorithm. And we can see that the binary bus algorithm is much faster than the rest of the algorithm. And also, VS bus is the second fastest algorithm. So by increasing by little the time consumption of the B bus, we are able to increase the the performance of the binary bus algorithm. Next, we move on in maximizing the Sharpe ratio. The Sharpe ratio divides a portfolio excess return by measure of its volatility to access a risk-adjusted performance. Excess return are those above an industry benchmark or the risk-free rate of return. So here we have the time-varying tendency portfolio optimization under non-linear constraints, which is presenting in this slide. So in the objective function, which is in the first equation, we try to minimize the transaction cost and at the same time to maximize the Sharpe ratio. Here, h of t includes the h sub I of t, where h sub I of t equals 0 if the variance of h sub I of t is lower than the parameter a, otherwise is 0. So in the application of this problem, we use the stock close prices that present in figure 17. So we have a market of 40 stocks from the period February 2020 to June 2020. So given an initial portfolio and using the settings presented in this slide, the results are the following. So figure 18a shows the Sharpe ratio, where we can see that Sharpe bus has the highest Sharpe ratio. And figure 18b shows the transaction cost, where again we can see that Sharpe bus has the lowest transaction costs. Figure 19a shows the average Sharpe ratio, where again we can see that the Sharpe bus has the highest Sharpe ratio, average Sharpe ratio. And figure 19b shows the average transaction cost, where we can see that the solution produced by the Sharpe bus has the lowest average transaction costs. Table 4 shows the time consumption, where we can see that Sharpe bus is much faster than the rest of the algorithm. So the Sharpe bus is the most efficient algorithm in this application. Next, we move on to minimizing the portfolio insurance costs. Portfolio insurance is a hedging strategy which is used to limit portfolio losses without having to sell stocks when stocks decline in value. One way to decrease a portfolio spending is to minimize its insurance cost. Consequently, the minimization of the cost related to the portfolio insurance is a very important investment strategy. So first, we must define the insurance prices, where we consider that P sub I of t equals a fixed price plus a price associated with the variance of the normalized price of the stock prices. So in this way, the insurance prices become more realistic. So the first problem here is the time varying CPI problem, presented in equation 48 to 50. So in equation 48, we want to minimize the portfolio insurance prices. And in equation 49, we want to keep the portfolio return above the specific floor price. So in this application, we use the stock close prices presented in figure 20. So we have a portfolio of 3 stocks from the period May 2019 to October 2019. So given an initial portfolio and floor price and using the setting presented in this slide, the results are the following. Figure 21a shows the portfolio weights, where we can see that the neural network solvers produce identical solution to QuackProp. Figure 21b shows the portfolio insurance cost, where we can see that the optimal portfolio insurance costs are much lower than the initial portfolio. Figure 22a shows the portfolio payoff, where we can see that the optimal portfolio payoff is above the floor price. And figure 22b shows the error between the solvers, and here we can see that LVI PDNN, the solution produced by the LVI PDNN, is closer to a QuackProp solution. Table 5 shows the time consumption of the neural network solvers, as well as the quad-proc. Here we can see that LVI-PDNN produces faster results for the nearest neighbor and linear interpolation method, while ZNN produces faster results for the piecewise cubic Hermit and the cubic spline interpolation method. Quad-proc was always much slower than the neural network solvers. And the next problem is the time varying CPI and the transaction cost problem, which is presented in these equations. And here we want to minimize the transaction, we want to minimize the portfolio insurance cost and at the same time the transaction cost of the portfolio. We excluded the payoff from the payoff of the previous time step. So in this way, the problem becomes more realistic. In this application, we use the stock prices, close prices presented in figure 23. So the market includes 4 stocks from the period October 2018 to January 2020. So given an initial portfolio and using the setting presented in this slide, the results are the following. Figure 24A shows the portfolio weights, where we can see that each algorithm produces a different optimal portfolio. Figure 24B shows the portfolio payoff, where we can observe that the payoff is above the target price. Figure 25A shows the insurance cost, and figure 25B shows the transaction cost. Again, we can see a similar behavior between the algorithms, with the exception of the genetic algorithm, which has a much higher transaction cost than the rest. And the time consumption of these algorithms are presented in table 6, where we can see that the bus was faster than the rest of the algorithm. Last, we will move on to the multi-period MCPI and the transaction cost problem. Here we want, which is presented in the equation of this slide. And here we want to minimize the portfolio insurance costs and at the same time the transaction costs. In here, the difference with the previous problem is that we included sub-periods. So we measure a period with many observations instead of just one observation. In this way, we differentiate the problem with the previous problem, and becomes even more realistic considering whole sub-period in our problem. So the market here includes the 8 stock presented in figure 26 from the period May 2020 to July 2020. So given an initial portfolio and all price, and using the setting presented in this slide, the results are the following. Figure 27A shows the portfolio payoff, where we observe that Firefly algorithm has the highest payoff, and BAS algorithm has the second highest payoff. Figure 27B shows the portfolio cost, where we observe that Firefly algorithm has the highest portfolio cost, while BAS has the lowest portfolio cost, which means that BAS produces a better result than Firefly algorithm. Table 7 shows the time consumption of the algorithm, and we can see that BAS was much faster than the rest of the algorithms. So to summarize, in this dissertation, we took popular financial problems, which are the minimum cost portfolio insurance, the mean variant portfolio selection, the Black-Litterman portfolio optimization, and the Tangents portfolio, and convert them into time-varying analogs. So on one hand, we convert them directly into time-varying analogs and approach them with ZNN and LVI-PDNN solver in order to produce their online solution. And on the other hand, we added nonlinear constraints to the static problems and then convert them into time-varying problem formulation, and then we approach them with mass variation in order to produce the online solution. So, with the technical contribution of the current doctoral dissertation presenting, we may now reflect on the milestone of the entire effort in the direction of time-varying financial modeling and the application of intelligent algorithms. Portfolio management is one of the most important subjects in finance, as seen by the engagement with prior work. So, because of the rapid advancement of computer science, as well as modern information technology and financial development, it is clear that more advanced technology and financial development, it is clear that more advanced computational methods for portfolio management can be developed. In the current dissertation, we have verified the above observation, both in terms of portfolio modeling and computational method, especially for the case of time-varying dependent variability. So the scientific and social impact of this research, of this dissertation, is that the online solution of the time-varying financial problem is a great technical analysis tool, as well as an important financial tool. New methodologies and algorithm procedures are introduced in the field of finance, and the online solution of the time-varying financial problems, along with fundamental analysis, will enable the investor to make better decisions. That is, it will enhance the process of evaluating finance-related transactions to determine their performance and suitability. Last, this doctoral dissertation led to 10 publications in the following journals and book series. It is important to mention that 4 of these journals are ranked as Q1. And thank you for your attention.
Okay, thank you, Spiros. I think we can move forward and give the opportunity to the committee to ask questions or make comments. I think we can start with the guest we have from the foreign university, with Professor Stanivirovic. And Pierre Predrag, if you have any comments or questions to make to Spiros, we can hear you.
Of course, I have some comments. I have some warm words to say about my cooperation with Spyridon. Before all, I would like to thank the National and Kapodistrian University of Athens and the dissertation supervisor, Professor Vasilios Katsikis, for my participation in the development and defense of this doctoral dissertation. It is my great pleasure to have participated in the preparation of this dissertation. I was a member of the advisory committee, and now I participate in the 7-member examination committee. My scientific cooperation with Spyridon was a useful experience and a great pleasure for me. Our scientific cooperation started in 2020. So far, we have published 18 common scientific publications. These publications include 11 Q1 journals, such as IEEE transactions on fuzzy systems, IEEE transactions on neural networks and learning systems, applied mathematics and computation, mathematics and computers in simulation, computers and operation research, mathematics, and so on. My cooperation with Spyridon has been enhanced during the Erasmus Plus study abroad program, 2021-22. From October 2021, Spyridon visited the University of Niš during our academic semester for the elaboration of scientific research. Our time at University of Niš was highly productive and initiated several joint publications and provided innovations and new results to strengthen dissertation. Moreover, our cooperation was expanded within the mega grant program of the 9th stage in Russian Federation. More precisely, last year, our mega grant project, Hybrid Methods of Modeling and Optimization in Complex Systems, has been accepted by the Ministry of Science and Higher Education of the Russian Federation. Our publication in the frame of this project about time-varying minimum cost portfolio insurance problem in applied mathematics and computation reached popularity in newspaper articles. General overview or observation about the dissertation is that time-varying shortly TV versions of popular financial optimization problems are introduced. The proposed time-varying versions of the financial problems are novel approach with respect to corresponding static financial models considered so far. Online solutions have never been applied before in the field of finance. The financial models investigated in these dissertations are portfolio selection problems, and they are classified into two categories. First category includes time-varying linear programming, LP problems, and time-varying quadratic programming, QP problems. Another strategy includes time-varying nonlinear programming problems and time-varying integer linear programming problems. Two strategies are separately proposed and applied in the development of online solutions. TV, LP, and QP financial optimization problems are approached by two continuous time NN solvers. TV, NLP, and ILP financial optimization problems are approached by popular meta-heuristic optimization problems, mainly belonging to nature-inspired algorithm termed as Beetle-Anthony search, BAS shortly. My first comment is about applicability of different techniques. So far, the two proposed techniques, neural networks and BAS, have been applied separately. On the other hand, a hybridization of BAS and ZNN has been introduced in some recent papers, resulting in a continuous time enhanced variant of Beetle-Anthony search, shortly BAS ZNN. What is your opinion about the applicability of BAS ZNN in solving TV, LP, or QP financial optimization problems? These problems were solved by neural networks so far. Do you think that the BAS ZNN iterations could overcome the limitations of the proposed NN solvers for LP or QP problems. Vasilis, what is your strategy? Can I state another comment or answer first?
I think it is better to answer the first comment and then we continue to the second and so on.
Mm-hmm.
Okay, to answer your question, I believe that bus ZNN might be a great future project for dealing with time-varying linear and quadratic programming financial optimization problem. In general, BusWAST is computational fast since it combines the parallel processing capability of ZNN with the adaptable random searching characteristic of BUS. It is important to mention that such algorithms must be specifically tuned to each unique problem for maximum performance. Therefore, under the right tuning and adaptation to each time-varying quadratic linear and linear programming financial optimization problems, BUS ZNN should outperform ZNN. Keep in mind that we want to increase the realism of the financial optimization problem. So time-varying non-linear programming and time-varying integer linear programming financial optimization problems are more preferable. However, a drawback of BUS ZNN, like ZNN, is that it cannot address integer linear programming problems.
Okay, if you are satisfied, Predrag, we can move to the next question.
Yes, I'm satisfied.
Okay.
Yes. My second comment is about integration of fuzzy parameters into relevant upgrades of ZNN design and BUS algorithm. You mentioned in your thesis that it is interesting research topic for future research. Moreover, it is known that fuzzy logic evaluated in neutrosophic logic, which is based on 3 membership functions: truth, falsity, and indeterminacy membership functions. Applications of neutrosophy in improvement of ZNN design has been investigated recently. We published, I think, 2 common papers in IEEE transaction fuzzy sets and neural I cannot remember name of the journal. Neural processing letters. Do you think that neutrosophic logic is applicable in improving the BUS algorithm? How can the impact of 3 membership functions be explained in the natural behavior of beetles in the BUS method? This is my second comment.
Okay, Spiros, your answer?
Okay, I believe that neutrosophic can be used with BUS algorithm, and particularly in 2 ways in improving the BUS algorithm. So one way is to use neutrosophic to measure the objective function error and modify the penalty parameter of a penalty method when dealing with constraints. And another way is to improve the Beatles antenna searching behavior through a neutrosophic controller. In both cases, neutrosophic membership functions will be used to tackle uncertainty.
Okay. Predrag?
I am satisfied. I want to congratulate to supervisor, Professor Vasilios Katsikis, and congratulate to candidate for such a good dissertation confirmed by numerous high-quality scientific publications.
Okay, thank you. Anyone other from the committee that wants to make questions or comments about the dissertation? Dimitra, yes.
So I would like to congratulate Spyros for the excellent presentation today and for the interesting topic of your research. I'm completely done from the previous comments, but I would like to ask you about your research findings, if there are any that surprise you after your findings have been done. How was your feeling after your applications of the real-world data sets? Are there any research findings that you expect something different, or how was your feeling about them?
Spyros?
So the results in the specific financial problem were expected, but in order to produce these results, we dedicated a lot of time and effort.
Mm-hmm.
So, yes, we try our best, and the results were as expected. Now, in terms of the applicability of the solvers, because this was our main focus, unfortunately, we couldn't use the neural network solvers to approach integer linear programming problems and mostly non-linear programming problems. However, our future project include using this kind of neural network solvers to approach non-linear programming problems.
Okay, yes, thank you. So, in my opinion, this is also a kind of any limitations that may exist in this current research. But in terms of your future studies, you could also say that you could overcome any kind of these challenges that exist, right? So, in order to proceed further for your future studies of this topic, what do you think?
Yes, that is correct. This is our goal.
Perfect. Okay, yes. Thank you very much.
Okay, thank you. Anyone else that wants to ask questions or make comments?
Vasilis, can I ask something? Yannis.
Of course.
First of all, I would like to congratulate the candidate. This work was very thorough, and I think that the presentation was very good. The number of publications justify all his effort. I would like to ask you something. As I have gone through your dissertation and your presentation, I would like you to ask you that the proposed methodologies are mainly benefit in time, as far as I can understand. You propose new methodologies that they are far more, not far more accurate, but because I think you, as an accurate solution, you have used some other kind of solution, but mainly it was the new proposed methodologies performed similarly to others, but mainly they were much faster. Isn't the case? Something which is very important to your applications, of course.
Yes, at some point I mentioned it during my presentation that in our result we used the default settings in the ODE solvers. This kind of neural network types uses MATLAB's ODE solvers. So we used the default settings, and as a result we have an error between 10 to minus 5 to 10 to minus 4. If we adjust the absolute and relative tolerance, which have done this in our papers, we can decrease this error down to 10 to minus 20, 10 to minus 30. So the time consumption is not also increases, but not that much. And if we measure the error of the error function, not the error between the quad-proc solution and the solver error, we can achieve much lower result than the quad-proc function. Of course, this is also included in our published paper, but I didn't use it in this kind of result in the presentation.
Thank you very much.
I would like to add something, taking the opportunity here. This thesis has two main parts. I can separate the part that deals with the computational methodology, algorithms, and this has to do with efficiency of the algorithm, speed and stuff like that Yannis mentioned. But there is another very, very important part. All of the economic financial problems that Spiros presented before, all of them until now in the literature, it was static. Everything was considered static. All was solved statically. Here we have defined these problems in a time-varying manner, and we try to solve them. This was very, very difficult to find the right methods that can solve such continuous time-dependent problems. And that was the problem in the bibliography until now, that those problems are hard to solve even in the static case. And we convert them in a time-varying manner, and we try to solve them with some computational methods, modern methods like metaheuristics and neural networks. So, in my opinion, there is a part that deals with computational speed of the algorithms and of the methods, but there is another important part that is the problems themselves and the way that we are dealing with them in a time-varying manner. Okay. Any other questions, comments from the other members of the committee? Dimitra.
Just to say something
okay,
about...
Hara also, next will be Hara. Okay, thank you.
Thank you.
Just
thank you very much. This is in the sense that what you have said already, Vasilis, is that it is really clear and crystal clear that the approach that you used reveals something more than the previous approaches. And it was really interesting that you mentioned about the time-varying manner and the ways that you dealt with the problem. So just it was something that I wanted to ask before, that there's any comment or answer about the approach that what has revealed and other approaches didn't before. So I think that I'm done with the comment that you gave, and again, many congratulations, Spiros.
Okay, thank you. Hara.
Yeah. First of all, I want to congratulate the PhD candidate This thesis is of high scientific quality, and it is well written in the sense that other researchers can read it, is self-contained, and they can inspire to continue the work. Under the supervision of the advisory committee, he has incorporated mathematical and computational techniques in portfolio management in a time-varying mode. And there is no doubt that the candidate is a very highly productive researcher. And I wish to him to continue this very good work. Congratulations, Vasilis, Advisory Committee, Spyrίδων Murtá, for this work.
Thank you, Hannah. Thank you. Thank you very much. Other comments? Okay, so then we can conclude our discussion here. I will ask Spyros to leave us, and Κώστα, σε παρακαλώ πολύ, κλείσα και το YouTube για να μπορέσουμε να κάνουμε μια μικρή συνεδρίαση. Okay. Okay. Spyros, thank you.
Okay, thank you very much. So I can leave now.